system from the NASCAR photo, and I'm here in collaboration with my fellow researcher, João from the Research Center in Digitalization and Intelligence Robotics from VDB. We are here to present the following article: Position estimator for a follow-line robot, the comparison square and machine learning approaches. The problem that originated the study for this article was that in Portugal there are several different competitions that are aimed at very young audiences. These competitions involve the utilization of a small differential traction robot that uses a follow-line control algorithm in order to accomplish several different tasks. However, since there are very young participants in this competition, it is necessary to adapt the different algorithms that we use in order to make them easily accessible and easily understandable by the young participants. This robot uses a sensor rack of 5 sensors placed in that configuration in Figure 2 in order to follow a line and control its movement along the several different black lines that are in the track. However, in order to accurately move the robot and be able to accurately control it, it is necessary to first calibrate these sensors for the luminosity and the track that the robot is being used on. The first problem that we faced was how do we accurately localize the robot in line based only on the 5 sensors that we have. If we use a digital data acquisition, as seen in Figure 3a, there are going to be places where the robot is on top of the line, but no sensor is currently detecting anything. Therefore, it's not a suitable approach. However, if we move to an analogic data acquisition, we can see that if the robot is on top of the line, there's always one sensor that's detecting it. However, in this case, there's a high uncertainty where the robot could be, since the area that are just mapped by one sensor is very high. Therefore, we opt for using a gradient line in conjunction with a manual data acquisition of the data. This allows us to compress the overall sensor data and be able to have at least 2 sensor readings for each of the points where the robot could be, with the exception of when the robot is fully off of the line. The second problem we face is how we are able to find the ground truth of the position of the robot in conjunction with the line in order for us to then be able to use our calibration algorithms and also be able to calibrate this on the field. The solution we came up with was the following test bed. We would use a small camera pointing down that's connected with a Raspberry Pi, and with the use of the Ruko markers and the Ruko marker localization software, we would be able to localize the position of the robot in a certain differential that we can then convert it to the distance from the robot center to the line. As you can see in the following image, that's the schematic of the test bed and the real image of the robot in one of the scenarios that we tested. The first algorithm we tried was the least square calibration. This algorithm is based on the ordinary least square method that's normally used with experimental data and observational data. And it will use as an input the matrix composed from the 5 readings of the sensors. As you can see, the matrix starts in the sample 0 and goes to the sample n, depending on the number of samples that we are using. And the output matrix is the x, y, and the theta, that represent the x coordinate, the y coordinate, and the theta coordinate of the robot in our coordinate system. We then used the data that we acquired from the ground truth to calculate the estimator parameters. These parameters were calculated in the following equation, presented in equation 1. And then we used the matrix that those parameters delivered us in order to estimate the real operation of the robot and get the real estimated coordinates of the robot, and then compare those coordinates with the ground truth. As you can see here is the first example where after we calibrated and after we obtained the parameters from the estimator, we then did another test in a different with a different movement from the robot, and as you can see, the estimator was able to estimate that accurately the distance from the robot center to the center of the line.
Well, then other approaches were tested to predict robots' location using machine learning methods. This type of methods has recently undergone significant advances, guaranteeing encouraging results even with small training datasets. Having the generalization as its working principle, these methods use the model training data, the experience, that provide essential features of the problem to formulate a function from a set of hypotheses. The selected function is subsequently used to label all instances, including unseen examples, the test data. Since it is a regression problem, here there is a need to predict the location of values. The decision tree regressor method was chosen, taking into account its easy interpretation and also its training speed. This method is obtained by recursively partitioning the data and fitting simple prediction model within each partition. As a result, partitioning can be graphically represented as a decision tree. In image 8, it's possible to verify the real regression tree of the present problem. Here, several divisions are performed according to the values of our input data, and the prediction error is demonstrated by the square difference between the observed and the predicted values. In this way, it is possible to perform position prediction for any input data sets. To implement the decision tree regressor algorithm, the dataset previously present by my colleague was used. This set is composed by 137 values referring to the robot's position, the output matrix Y, if you remember, and also the data line of the sensors, the input matrix X. Once the training dataset to the model was established, some of its hyperparameters like max features and min sample width were also optimized. In this case, we are using the function research-CV implemented with a 10 times cross-validation. By way of comparison, the prediction was also made using the same dataset combined with a simple linear regression method, without any kind of optimization. To test the effectiveness of the two algorithms, the predictions of the robot position Y was performed from a dataset totally new to the models. This new dataset derived from another simulation, and it was composed by 114 entries. The results of both algorithms are shown in figure 9 and 10, and as it is possible to see, there is a clear advantage in the use of linear regression in the decision tree regressor, since the estimate values by the predictors are very approximated with the ground truth values. In addition to the results obtained with the test set present before, and considering the variation of readings given by the line sensors, 4 different situations were simulated to amplify the test set, and thus test the effectiveness of the prediction models for new types of readings. To facilitate this evaluation, the usual metrics were used: the root mean square error, the RMSE, and the coefficient of determination. In this way, the input matrix X was modified, and after its modification, the robot's position were predicted. The changes tend to simulate the different types of reading, thus testing their behavior in various types of sensors and other reading conditions, like kind of different luminosity and also different line intensities. The first changes affect all of the readings, increasing and decreasing the values by 20%. Then, 2 new readings were simulated where only the central sensor was decreased and increased by 20%. This results in 4 different test sets that aim to cover the various possibility readings of this type of sensors, noting that in all the test sets, the output matrix Y remains similar. The results are present in the table 1, and here it's possible to notice a clear advantage in using the decision tree regressor method, noting that values closer to 0 in RMSE metric are better, as there is a perfect forecast with RMSE equal to 0. On the contrary, the R squared equal to 1 is a 100% correct prediction. The results obtained through the simulation were also encouraging when we observed that, in general, the results are very similar to those obtained with real data, thus allowing to mention that the prediction continued to be admissible for a different sensor screen. Well, in this presentation, we talk a little about the 2 methods for the position estimation of a robot using the data from an optic line sensor array. It was used an image-based system to localize the robot in the testbed environment, and both methods, the least square and the machine learning, were implemented and tested in the real scenario. Here, a gradient line is used to get the data from the line sensor. Results are promising and show that even with a limited amount of data, the system was able to forecast values very close to the ground truth, even when using simulated values of the real sensor readings. As a main future work, the implementation of both methods in the embedded system will evaluate the required computational resources like memory and processing time, and it also will address the availability of each method to implementation with limited hardware resources. Well, this is the end of our presentation. Regretting that we could be in person, but always available for any question or suggestions that may exist. Feel free to contact us.
I don't know if one of the authors is present in the Zoom, but I don't believe. I don't see any name here. So questions are possible, but answers are not. So probably we go to the next one. And the next one is, let's do this. You know which one is? This one? Okay. Just starting the process. So the third one, and we are a little ahead of time, so that's good. Remote VDB mapping, a level-based data reduction framework for distributed mapping. Marvin Gross Brasham will be presenting. I'm sorry for not pronouncing your name correctly. Let's just, oh, sorry. Too early. There's this one.
Okay, good day everyone. Today I want to talk about remote VDB mapping, which is an extension of our mapping framework, VDB mapping. First of all, why do we do that? Recently, actually quite last week, we participated in the final round of the ESA Space Resource Challenge, where it was the target to prospect resources on the moon. And they built up this nice environment for us in a concert hall, which had a lot of craters and other stuff in it. So quite challenging terrain. And we had to autonomously find resources there. So basically we needed a path planning in complex environments, and which also covers dynamic changes of the area and fast obstacle avoidance to avoid each other, because we participated with a team of robots. I don't know if we can see them in the lower left, lower right image. We had an animal and a spot robot and a Husky platform for science equipment. And since we want to use the full 3D space for the path planning, we wrote VDB Mapping, which is a volumetric mapping framework based on VDB, which is a quite fast data structure for voxel representations. So basically it abstracts the raw sensor data into a grid representation and has infinite, well, literally infinite index space. It's only restricted by the amount of RAM you have on your PC. And it is quite fast to integrate new sensor data with it. And you can access the generated maps also quite fast. We also open sourced the whole framework as a core library and a ROS1 and ROS2 wrapper if anybody is interested. And yeah, here's also a video of the current approach, which isn't starting. Damn it. One moment, please. Yeah, here we have a spot robot walking through our lab and integrating all the data in real time. I think it's completely integrating every data with the 10 hairs of the Velodyne, which is mounted on top of it without throwing away any data. So we have a huge, complete map representation of our environment inside the robot. Yeah, but the main problem is those maps get quite large at some point. I mean, not in small scale environments, but the arena for the Space Resource Challenge was like 40 by 60 meters, which is a huge amount of data for a 3D grid. And also, since we had robot teams and well, we had actually three robots, which all generates their own maps and a remote base station from which we had to control all the autonomy levels of the mission. And there we also wanted to have a representation of this map. So basically the problem was, how do we get the map onto the base station, and that efficiently, because the network was first of all restricted to 100 mbits per second, and also it had a delay of 5 seconds to simulate the communication lag to the moon. So the problem is we can't really send the complete map over this network. And the idea behind now is, how can we reduce the data we have to send there? So first, I want to say how the normal process of the VDB mapping work. First, we raycast all sensor data into an update grid. This sidestep is necessary so we avoid issues with discretization errors and stuff. And afterwards, we iterate over this update grid and make the probability update for the map, at least for each cell of the map. So the idea now, with a naive view, you can just say, okay, let's just send the map over it. But as I said before, it gets quite large soonish. So we split it up into different levels of a remote mapping approach. Level 0 is kind of not really such a data reduction. It's more like a computational power reduction for drones and stuff, which don't have that much computational power, because here on the local machine, we raycast the update grid as well and can send the whole update grid and only do the integration into the map on the remote side, which lets us avoid the raycasting process on the remote hardware, which is quite resource intensive. But still, in this case, we still have a transmission rate of around 6 MB per second, depending on the sensor data amount and the raycasting distance. On level 1, we just, we only insert all the endpoints of the sensor data into an update grid as well. These update grids can be, well, compressed quite huge, quite nice, and that great, large. And then from that on, we do the raycasting on both parts to generate the same map on both ends. Here we also have a data reduction of only 1.2 MBs per second, which is better. And the level 3 is mostly only for visualization purposes, because in this case, we do the complete mapping pipeline on the local robot. But during the update step, we extract the difference between the two maps because I mean the T-1 map and the T0 map, and send only this over the network, which is really, really small. And we could achieve around 500 kilobits per second. And then just override the map on the other side. This has the problem that the whole probability framework of the mapping approach is lost on the remote side, but still for only visualization purposes, it was quite enough. Yeah. So in conclusion, we presented a level-based data reduction, which is drastically reduces the transmission bandwidth. And we also are able to reduce the computation of the maps on remote machines. But actually during the Space Research Challenge itself, we found out that package loss is a huge problem for the visualization part, because if we drop the overrides, the changes in the map, they only got sent one because the voxel changes only once, and then it's either occupied or free if it's not a dynamic environment. And so if there happened a package loss, the map isn't complete anymore. So after, well, it's not in the scope of this paper anymore, but we also improved on that by continually syncing the map with larger patches of the actual map, which also isn't that much of a data bandwidth if you don't do it too regularly. So yeah, that was my presentation. And
thank you for your presentation. We are open to questions now. No questions? Oh, please.
Have you done any benchmarking to compare the different bandwidth, the performance for the different? Understand?
Yeah, there's a table of different approaches with different resolutions. Was it that what you mean? Or?
In terms of performance in navigation, or in you just tested the resolution?
Yeah, I mean, for that it was just the only variable was the resolution. There, I mean, we have all the levels there, but we didn't check it on many different. We didn't evaluate on many different scenarios there. I just had a back file of our lab environment where I tested those.
Thank you.
Okay. Any more questions? We have time yet? Yes.
Thank you. Somehow related question to that one. Most of the things you mentioned had to do with how it shows the appearance when you send it and lose resolution. But did you test it, how much you lose regarding, imagine you have a team of cooperating robots and the other one wants to use the map you did for localization. Mm-hmm. Did you test the impact of the loss of resolution on that or something related?
Not specifically. The mapping just happens before after the localization. For the localization, we also use another approach, which isn't related to the mapping at all. So we didn't really dive deeper into that.
Thanks.
Thank you for the questions. we still have time, so if someone else needs or wants to, okay. I have a small question. I believe you present a nice way or a better way to transmit data, to be exact, the map of the environment where the robot goes. And I would like to know if if you test the limits of this technology. How much can we go to the resolution of the map?
In our cases, we mostly use a resolution of 0.5 centimeters for the map, which is mostly due to the running navigation on there, because this takes more time the lower the resolution, higher the resolution is. So basically, about 1 centimeter with a, I mean, we tested it in the initial paper about the mapping. If you go below 1 centimeter with a standard Velodyne or something, the integration process takes quite a bit of time, like a second or something for new sensor measurement, which isn't like real-time capable then anymore, since we want to integrate the data quite fast to avoid upcoming obstacles.
Okay, thank you. Any more questions? Okay, thank you for the presentation and for the answers. Now we have online presentation. I don't know if there are someone here to present. Let's see. Where it is. There are someone at home to present the fourth presentation or not? How can they communicate with us? I don't believe. So probably we have our first no-show for this conference. Nobody's trying to communicate with us, I believe. So I just finished the presentation. For now, we have the next section at 12:30, 12:30. Okay, thank you. for lunch. Second section is named Robots in Education and Educational Robotics. The first presentation is called Machine Learning Application with a robotics tool, what we learn from pilot studies. Will be present by Amy Egeshi. Sorry. Thank you. I have to share. Yes. No. You want to send it? Really sound?
Oh, yeah. Oh, good. Hi. My name is Amy Gucci. I'm from University of California, San Diego in the US. And I would like to thank the organizers for giving us an opportunity to talk about educational robotics, because we don't really have that many opportunities, especially to the audience who are really in the field, robotics scientists. So I want to thank for the organizer for the opportunity. That's the reason I'm here all the way from San Diego, 20 hours trip to be here for 15-minute presentation. My presentation is not going to be with numbers or formulas or algorithms, so just relax and listen. And then if you can agree with me, it's going to be great. So let me just give you a little bit of a background. AI is everywhere in the kids' life and our lives. It's hiding a lot of different places, but a lot of times kids don't know. And especially if you talk to elementary school kids, preschoolers, they think AI is magic. Is it really a magic? That's where the whole conversation we actually started amongst the educators. What should we do about it? And especially we want to really focus on the code biases, algorithm biases, AI ethics, because the way, sorry to say it, the kind of people involved into creating algorithms, less than half of the population, I'll guess, meaning mainly usually white, male dominated field. And my passion is to how to make this field more diverse, to involve many different people, from women to people of color, minority people, because especially at the end of the day, not now though, but in the future, everyday people will be using AI in their everyday lives. And if they don't really fully understand what it is and how it's working, it's a bit scary in the sense that the people is going to be just a consumer of the technology than the user of the technology. So that's where this whole argument about, okay, we need to teach AI literacy to kids, and there are a group of people all over the world figuring this out, and there are like text here and there, but in the center, we meaning there is a group called AI for K-12 initiative in the US. It's an NSF-funded National Science Foundation funded project to come up with a guideline for educators to cover different components of basically big ideas of AI. So this is out there, and then we're figuring out what's the best way to teach it. And And then also, this is in the US, but we have been having workshops and PAD for teachers to introduce different way of teaching with lesson plans and activities. So we have been doing it. And the new one coming up is going to be in December. I'm also part of it. CS is Computer Science Education Week. That's a big teacher-focused computer science education organization. And the one that I want to talk about today is, okay, take it back a little bit. We need to teach AI and AI literacy, we need tools. And my focus is computer science, robotics, AI education. And one of the things that I have been exploring is this little robot, which is, the sensor is Android phone. And we usually use the Android phones that nobody uses anymore because it's like 3 generations old. And so we use those with a Arduino board, simple DC motors to really figure out how kids can actually play with machine learning technology. And I don't know, it's 10 minutes, right? Or 15 minutes. There's a little video. Of course, I can't read it, but I'm just gonna say yes. Oops. Okay. So
I'm the UNESCO educational robot built with Google and powered by Infinix. Let me do some warm up here.
So this is how it looks.
Okay, I'm ready. Show me an object.
The reason why I started to, I don't know how to get back. I think I need to move this down. Okay. Yeah, that's fine. Oh, maybe here. Okay. Because it's really less expensive. Even you buy all together 3D print, it's $300 or even less than $100. So that's why this is practically good tool. But my question was, okay, how can we use this? So I started out with doing a little exploration kind of project with middle school and high school kids. And of course, middle school and high school kids get really excited. And I started to use it. For the machine learning part of it, we use something called Teachable Machine. I don't know how many of you know Teachable Machine. It's a Google tool, really simple. Amazingly effective tool to actually for kids to train a machine learning model. But then if you don't apply it, that's that, just playing with it. So this tool allows kids to use the trained model with a robotic coding, which is simple scratch extension. So block coding was a little bit of I just say yes. Yeah. This is how it looks. Is it this? This one. So scratch extension, this is all block coding. Scratch extension is that those extra blocks the developer actually created, and you can use that to use the trained model in this block coding environment. So we have done that. Then because kids are kind of, it looks like kids understand it. So I'm like, okay, so we should probably start creating the lessons. So I brought my undergrad students in to use a teacher. Oh, this is about Teachable Machine. So it's a Google tool. You can go and then take a look at it. It's really, really fun. But then when we started to bring the undergrad students in, all computer science majors, and then some of them actually took machine learning courses. They understand it better than I do, I guess. But then it becomes really hard because when you train the model, if the computer is stationarized and camera is just looking at one direction, think about how you use that model on the robot that's moving around. The background changes constantly. And my students, my kids, had a struggle a lot to figure that out, which I was surprised because I thought they understand it. So instead of using the desktop, maybe have a phone, taking the picture, moving around, or, but they just sort of stuck with this desktop idea. So they really,
okay.
Hold on.
So
it just happens right
here
away.
we can see
Having difficulty making the model that's sort of like perfect. So the first try around, this student was like, okay, so if the background doesn't have anything, so he started to use the cardboard and testing it out, it kind of worked.
So when I show it a yellow card, it should turn right or left, I forgot. Left. And then when I show it a red card, it'll turn the other way. And when I show it a blue card, it should go backwards. And when I show it a green card, it should move forward. But it's kind of getting confused there. So
yeah, so he's using the Uno card, different color, so it's like color coded. But he's saying blue and green are harder. It identifies a green, the blue, but the green is harder for the camera or the computer or this robot. And I think he didn't take the lighting into consideration. And actually, before this, I don't have the video of this, the other one. Before this, he was training a model when his computer was facing the window. Of course, the light is coming in. And then he was using the model on the robot in the box. And then, of course, none of them worked. Right? I mean, it makes sense to us or the people who actually have an experience, but he did it because for him, computer science major, everything is on the computer. So he had never done robotics before. So this was a sort of mind-blowing experience for him. So, and then I had 2 computer science majors. There's still 1 more quarter left. So they're coming up back in fall, and then they're gonna actually work more. But it actually it gave even the undergrad students who have trained to understand the machine learning and algorithm struggle, which was interesting. And if you can go to the presentation, I had a QR code at the beginning. There's a Python code he created so his next idea was to take a video using the phone and use the video using the Python code to convert the video into multiple pictures. So slice it out and then just take the picture files and then use that picture file, upload to the machine, teachable machine, and then train a model. And he thinks that's actually better. And then I always have to remind them, well, at the end of the day, you have to create a lesson for high school kids. So you have to be able to explain that. And then they're like, okay. So we'll see what's gonna happen in fall. But this is just before the summer, this is what they were doing. So now Lobo is not moving because they're not so into now making a perfect machine learning model, which is okay for me. Because it's more like for me is an exploration of what kids will do. Kids meaning the undergrad students. So this is the video just before summer.
The result is pretty stable. And the result is empty.
So empty bottle. So if it's empty, the robot says empty. You can really read it. And it's going to be halfway full. I don't know why they wanted to do this. And then if it's halfway through, then the robot goes half. It shows half, but it's half is less stable than full. If it's full, we'll usually identify it as full, but I'm somehow halfway, half empty.
We can see
it sometimes confuses a little bit. And their assumption is, I don't know why they're saying what they're saying. Their assumption is because there is a arm in the camera, but I'm not sure if that's true. But you can see that even undergrad students still struggling to figure that out, which is really interesting.
I think it's because
but
like,
so one of the students also said to me, well, my machine learning course instructor also said, even them professionals, they don't know what's going on, because in the middle, the hidden layers, they don't know what's going on. So that's why it's okay to not know what's going on. That's his argument, which is kind of interesting. But that's also something that younger kids also need to know. This is not like even some part of the machine learning is computer deciding. So there are that's why sometimes it's difficult for even the professionals to figure out what to teach and how to teach. But anyways, what we're trying to do